Welcome back. Our deep dive today is all about, well, escaping the limits of today's rockets. We're looking at innovative propulsion for true deep space travel.
Yeah, it's a huge challenge. I mean, chemical rockets are amazing for getting off Earth, right? High threat.
Absolutely. Big power.
But for the long haul, across the solar system, they're just not very efficient. You end up carrying tons and tons of propellant. It's that old tyranny of the rocket equation.
Right. The fuel itself becomes the biggest chunk of mass.
Exactly. So we really need new physics, new systems to crack deep space.
And that's what we're digging into. We've looked at sources covering three really promising areas. First, electric propulsion thing, high-efficiency marathon runner.
The long-duration specialists.
Then nuclear fission propulsion. That's a massive leap in power density we'll talk about.
A potential game changer for speed.
And finally, something almost poetic, solar sails, literally propelled by starlight.
Elegant, but with its own challenges.
Before we jump in, though, we need to talk about that key metric, specific impulse, sipping quick refresher for everyone.
Sure. Basically, ISP is the measure of rocket engine efficiency. It tells you how much push or thrust you get for a given amount of fuel burned over time.
So higher ISP means?
Higher ISP means you're much more fuel efficient. You can thrust for longer or go further with the same amount of propellant. It's crucial for breaking that tyranny.
Got it. Efficiency is king for long trips. Okay, let's start with electric propulsion, EP. These are the marathon runners, you said.
That's a good way to put it. They definitely trade that raw, instant power of chemical rockets for incredible endurance and really high efficiency.
So they sip fuel, basically.
Exactly. EEP systems use a tiny amount of propellant, usually an ionized gas like xenon or argon, and accelerate it using electric fields, often powered by solar arrays. They produce low thrust, but they can keep it up for months, even years.
And that enables missions that just wouldn't be possible otherwise, right? Like NASA's Dawn spacecraft.
Precisely. Dawn used ion thrusters. Because they were so efficient, it could travel to Vesta, orbit it, study it, then leave orbit and travel all the way to Ceres, another major body, and orbit that.
Wow, 2 deep space targets in one go.
You just couldn't do that with chemical rockets.
Yeah.
The fuel needed for that second leg, that big burn to get from Vesta to Ceres, would have made the spacecraft way too heavy to launch in the first place.
Okay, so EP opens up new mission profiles. Now let's get specific. Hall effect thrusters, HETs. These are pretty mature now.
Oh, yeah. They've got flight heritage. You mentioned Smart 1 going to the moon back in 2003 using HETs.
And now they're being used commercially, like on Starlink.
Right. SpaceX uses them on their Starlink constellation.
Yeah.
It's a great example of scaling up the technology. And it also highlights some interesting real-world trade-offs.
Oh, like what?
Well, traditionally, high-performance HETs use xenon. It's heavy, easy to ionize.
Yeah.
But Starlink initially used krypton, and now their newer V2 satellites use argon.
Why the switch? Just costs. Argon's cheaper, I assume.
It is significantly cheaper and more available than xenon. But there's a performance hit. Argon is lighter and takes a bit more energy to ionize about 14 electron volts versus xenon's 12.1.
So it's slightly less efficient. Needs a bit more power for the same push.
Kind of. You sacrifice a little bit of performance, maybe a tiny bit of operational lifetime or speed per satellite.
Yeah.
But when you're building thousands of them, the cost savings on the propellant are enormous. It's a classic engineering trade. Performance versus economics at scale.
Makes sense. But the thrusters themselves are getting better too, right? Higher efficiency.
Absolutely. Modern HETs are hitting efficiencies up to 75%, which is fantastic.
Okay.
And the power density, how much thrust you get for the engine size, is really climbing.
You mentioned JPL's work.
Yeah, JPL's H9 thrusters pushing the boundaries. They've tested up at 25 kilowatts. At 12 kilowatts, it achieved a specific impulse of 3,000 seconds.
3,000 seconds. Okay, remind us, chemical rockets top out around?
Around 450 seconds. For the really good ones, like the Space Shuttle main engines.
So 3,000 ASP, that's nearly 7 times more efficient.
It's a huge leap. That H9 test showed 2.7 times higher power density than the current best HETs out there. But for those really long missions, decades long, there's another hurdle.
Which is?
Wear and tear. The channels inside these thrusters erode over time from the ion bombardment.
So even marathon runners get tired eventually.
Right. So there's a lot of research into advanced materials, things like using nanocrystalline diamond coatings in the thruster channels.
Diamond, like actual diamond.
Well, thin films of it. Diamond is incredibly hard and wear resistant. Early tests show it reduces erosion by maybe 100 times compared to current materials. The goal is to get these thrusters to operate reliably for 20 years or more.
Incredible. So EP is perfect for those long, slow, fuel-sipping journeys. But what if you need speed and efficiency, like getting humans to Mars faster or sending bigger probes out quickly?
Yeah, that's where EP, even a high-power EP, starts to reach its limits for, say, rapid transit. If you need both high thrust and high ISP, you have to look beyond solar power.
Which brings us to harnessing the atom, nuclear propulsion.
Exactly. This is where we potentially bridge that gap. The main concept here is the solid core nuclear thermal rocket, or NTR.
Okay, break that down. How does it work?
It's actually conceptually simple, relatively speaking. You use a nuclear reactor, a solid core reactor, to heat up a propellant, usually hydrogen, to incredibly high temperatures. We're talking around 3,000 Kelvin,
Super hot gas.
extremely hot. And then you expel that superheated hydrogen through a nozzle, just like a chemical rocket.
Yeah.
But because the hydrogen is so hot and light, you get much higher exhaust velocity.
And higher exhaust velocity means?
Higher specific impulse. NTR's promise an ISP between 850 and 1,000 seconds.
Okay, so roughly double the efficiency of the best chemical rockets.
Double the ISP, yeah. And what's really interesting is why hydrogen is so good here. At those temperatures and pressures, the hydrogen molecules, H2, actually start to break apart or dissociate into individual hydrogen atoms, H.
So the exhaust gets even lighter.
Precisely. Lower average mass in the exhaust, which directly boosts your ISP. That translates into potentially cutting transit times, dramatically shaving months, maybe a year, off a crewed Mars trip.
Double the efficiency, faster trips. Sounds amazing. So why are we already using NTRs? What's the catch?
The big one is safety, specifically launch safety.
Right. Launching a nuclear reactor.
Yeah. The main concern is what happens if the rocket fails during launch and crashes, particularly into water, like the ocean.
Why water specifically?
Water acts as a moderator, slows down neutrons, which can actually increase the reactivity of the nuclear fuel. You risk an accidental criticality and uncontrolled chain reaction. That's obviously a major hazard you have to prevent, absolutely.
That's a huge hurdle. Politically, technically, everything. How do you solve that?
There are a couple of main approaches being worked on. One involves using poison materials within the reactor core during launch. These materials absorb neutrons and prevent a chain reaction until they're removed or deactivated once safely in space.
Okay, like a safety lock.
Oh, kind of. But perhaps the more robust solution involves in-space assembly and manufacturing ISAM.
Assembling it in space.
Yeah. The idea is you launch the reactor components separately, maybe not even fully fueled. For instance, you might only load certain critical fuel elements, maybe using that high-assay, low-enriched uranium fuel after the main structure is safely in orbit far from Earth.
Ah, so you don't launch a live reactor. You launch the pieces and put it together up there.
Exactly. Use robotics, assemble it module by module way out in space. It completely eliminates the risk of that water immersion criticality during launch. And we should remember, this isn't science fiction. The U.S. ran the NRVA program back in the 60s and 70s.
Right, I've heard of that.
They built and ground-tested highly efficient NTR engines. The program was canceled due to budget cuts and shifting priorities, not because the tech didn't work. It's proven technology, really, waiting for its time.
A technology ready for a comeback. Now, NTR gives you that high thrust and high ISP, but there's even more potential with nuclear, right? Nuclear electric, fusion.
Definitely. Nuclear electric propulsion, or NEP, is sort of the next step. Instead of using the reactor heat directly for thrust, you use the reactor's heat to generate a lot of electricity.
And use that electricity to power.
Those super efficient electric thrusters we talked about earlier, like Hall thrusters or ion engines, but scaled up massively. The goal with NEP is dramatic cuts in transit times for robotic missions, maybe even enabling faster human trips beyond Mars.
And the ultimate goal, fusion.
That's the dream for many. Direct fusion drive, DFD. If we can ever harness fusion power controllably for propulsion, you're talking about systems that could potentially offer both very high thrust and incredibly high specific impulse, maybe tens of thousands a second.
Tens of thousands, that's just mind-boggling.
It is. There are concepts, like the Princeton Field Reverse Configuration Reactor, that studies suggest could achieve this. For instance, getting to Sedna, that incredibly distant dwarf planet.
Way out there.
Yeah, DFD calculations suggest maybe a 10-year trip, operating at around 9,600 seconds ISP, and crucially, with enough power to actually insert into orbit around Sedna for detailed study, not just a flyby.
10 years to Sedna with orbit insertion, that really opens up the outer solar system. Okay, so we've gone from efficient electric cruisers to powerful nuclear rockets. Now let's shift gears completely to something fuelless. Solar sails.
Yeah, it's a beautiful concept, isn't it? Using nothing but sunlight pressure to travel. The idea goes way back to Tsiolkovsky in the 1920s.
Tremendous mirrors of very thin sheets, he called it.
That's right. And it's not just theory anymore. We've seen real successes.
Like Icarus from Japan.
Exactly. JAXA's Icarus in 2010 was the first to actually demonstrate controlled solar sail propulsion in interplanetary space, a huge milestone.
And the Planetary Society's light sail missions, too.
Yep, LightSail 2 in 2019 was the first CubeSat, a tiny spacecraft, to change its orbit using only sunlight, proving it works even for small scales.
And just recently, NASA had success with ACS-3.
Right, the Advanced Composite Solar Sail System. They confirmed deployment and operation of its 80 square meter sail just this past August 2024. So the technology is maturing, becoming more practical.
Okay, so how does it actually work? Is it really just photons pushing on the sail, like wind on a boat sail?
It is. It's solar radiation pressure. Photons, even though they're massless, carry momentum. When they bounce off a reflective surface, they transfer some of that momentum, creating a tiny but continuous push.
Tiny is the key word, I guess.
Very tiny, but continuous, and it requires no fuel. We measure the effectiveness using something called the beta ratio. Beta ratio.
Beta ratio. Okay, what's that?
Think of it like this. It's the ratio of the outward push from sunlight pressure compared to the inward pull of the sun's gravity.
Ah, tug of war. Light pushing out, gravity pulling in.
Exactly. So if your beta is, say, 0.5, the light pressure is half as strong as gravity. That's enough to significantly alter your orbit, leading to a parabolic escape trajectory from the sun.
And if beta equals 1?
Then the light pressure perfectly balances the sun's gravity. The sailcraft essentially ignores the sun's pull and can travel in a straight line away from it, or even hover at a fixed point relative to the sun. Beta greater than 1 means you're actively pushed outwards on a hyperbolic escape path.
Higher beta, faster escape. Simple enough. But I read about ways to boost the sail's performance beyond just reflection, something called thermal desorption.
Ah, yes. That's a really fascinating cutting-edge concept. The idea is to coat the sail with a specific material, often a carbon-based one, like fullerene C60 buckyballs.
Okay. And then what?
The mission profile gets clever. You'd launch conventionally, maybe get a gravity assist from Jupiter to swing you in really close to the sun, a perihelion pass.
Like close to the fire.
Right into the heat.
Right.
As you make that closest approach, the intense sunlight heats the sail dramatically. This heat causes the special coating to desorb, basically boil off the surface rapidly.
Creating a temporary rocket effect.
Exactly. It creates a jet of gas, giving you a significant extra push right when the solar radiation pressure is also at its peak. It's a way to get a burst of acceleration using the sun's heat itself.
That's ingenious. So, let's go back to Sedna again. We said the DFD fusion rocket might take 10 years, but could orbit. How does this enhanced solar sail compare?
This is where it gets really interesting. The studies suggest that an enhanced solar sail, using that Jupiter assist and the thermal desorption boost near the sun, could actually reach Sedna in about 7 years.
7 years? Wait, that's faster than the fusion rocket concept?
Faster transit time, yes. 3 years faster.
A fuelless sail beats a futuristic fusion rocket on speed. How is that possible?
It's possible because the sail gets that huge initial kick from the sun and desorption and then just coasts incredibly fast. And this is the critical trade-off.
Ah, there's always a catch.
There's always a catch in spaceflight.
Yeah.
The Enhanced Solar Sail mission to Sedna, the 7-year one, is basically limited to being a flyby, or maybe a very minimal probe. We're talking a payload of maybe 1.5 kilograms.
1.5 kilos. That's tiny. Like a couple of instruments on a chip.
Pretty much. Highly miniaturized sensors. You're sending back basic data, maybe some images. A scouting mission, essentially.
You're sending an advanced postcard, not a full science lab.
That's a good analogy. The DFD fusion rocket, while taking 3 years longer, can carry a much larger, more complex scientific payload and has the power to decelerate and actually enter orbit around Sedna for long-term, in-depth study.
So it's speed versus scope. Get there fast with minimal gear, or take longer but arrive ready for serious science.
That's the fundamental choice. And it perfectly illustrates the spectrum we've discussed. You have EP for the slow, steady, efficient long haul. You have nuclear fission for a big boost in power density and speed, enabling faster crewed missions or heavier probes. And you have solar sails for potentially very fast, fuel-less trips, but likely with smaller payloads.
It really boils down to that core tension in mission design. High thrust versus high specific impulse. Getting going fast versus being efficient for the long journey.
Exactly. You constantly have to balance those depending on where you want to go, what you want to carry, and how fast you need to get there.
And realizing that Perhaps the absolute fastest way to the outer reaches might be this elegant sail powered by starlight.
Yeah.
But it forces you to leave most of your scientific instruments behind. It really makes you think about what's essential for exploration. What knowledge would you, our listeners, be willing to sacrifice to shave 3 years off a journey to the edge of the solar system? That's the kind of question shaping the future of space travel.